the last two sessions, we mentioned the two different kind of way of converting from S domain to Z domain. So one method is the ideal sampler. So this is basically using the direct Z transform. And the second one is using zero odd hold, which is you put a zero odd hold plus the Laplace transform and do a Z transform of the whole thing. Okay, so you have to consider physically there's a zero odd hold in there. Actually, next week I'm going to choose a few other different ways to get from S domain to Z domain. So here is just two of the situation. The first situation is we wanted to make sure the impulse transfer are maintained. The second one is when you physically get a digital signal to analog signal, you physically have a zero odd hold. You have this function multiplied before the Laplace transform. Then you do a Z transform. Okay, so after those two, the rest of this week, I'm going to introduce the issues that coming from those sampling. So basically coming from the sampler and also zero odd. So you can see here, if we have a certain sampling time t, so if we have a sampling time t, so we've got a signal every this time period. So you can see the issue here is you have a black signal over here. There's a black signal that fits into these points exactly okay. Then you have another signal, this red dot signal, with a bit higher frequency. This one signal can also be sampled at exactly same sampling time and get exactly the same samples. So in this case, it's impossible to tell which signal are we actually doing the sampling. Okay, so you can see the issue here. If we can sample more, if we get more samples in between, then we can tell if it's coming over here, then it's the red signal. If it's coming over there, it's the black signal. But when we don't have enough sampling instance here, it's hard to tell. So to get more sampling points means you have to have a higher sampling frequency. So when the situation is the sampling frequency is not high enough, we will have certain situation you have multiple signals actually show up at the same kind of at the same kind of sampled data. So this is called we have a sampling theory which defines the sampling frequency must be at least twice as fast as the bandwidth or the height frequency contained in the signal. So sampling frequency Ws divided by 2 must be larger than the bandwidth of a signal. So normally bandwidth signal is from the constant to high frequency. So omega b is highest frequency within the signal. And this frequency, the omega, the highest sampling frequency divided by 2, we define it as a Nyquist frequency. Okay, so this can be restate that the Nyquist frequency must be larger than the bandwidth of the signal to make sure the alias doesn't happen. So you don't have kind of confusion between what signal are we actually sampling. Sampling itself is a time variant process. So we're talking about all the system where analyzing is linear time invariant system, so it means it doesn't change with time. However, the sampling itself is a time variant process. So if you start sampling from time equal to 0, or you start from time equal to 1/3 of the sampling period, actually you got the samples are different, which is easy to see from this figure. You can see if we start from 0, we have different instant. If you start from 1/3 of the sampling time, so it ends up to be taking different point from that curve. So the discrete signal of these two series are different. They have a small offset of this 1/3 of the sampling time. To understand why we have to sample at high frequency, higher than the Nyquist frequency, we have to look at the Laplace transform of the ideal sampler. So if you go back a few slides, you get an xt star, and here we take a Laplace transform. You can see the bandwidth or the frequency components in this sequence is integrating from a bunch of kind of different locations, from negative to positive, to negative infinity to positive infinity. It's all there. And if we take this s equal to j omega, means we only look at its frequency side of signal, only look at the frequency. We don't worry about the real component from the s. Then this one actually can plot it, and from the plotting here, things become very easy to understand. So this is the total frequency, and if we look at this one, start from t equal to 0, this is the frequency now. The horizontal axis is the frequency. So if we take this n equal to 1, you got this area. Okay, sorry, this is n equal to 0. You got this area. When equal to 1, you got this part. So this is a n equal to 1. This is n equal to 0. Okay, this is a n equal to 2. So you can see the matter here is, if we have our sampling frequency high enough, okay, because this is our sampling frequency. If our sampling frequency is high enough, this whole graph then will be spread out. So this will go right. Then you have this curve, this band, n equal to 1 and equal to 0, will be separated. So this will actually go in shifting to the right, because if we include omega s, this whole thing, this whole band will shift to the right. Then there will be no overlap with the previous one when n equal to 0. So this part, this curve, represent the bandwidth of the signal. So if our sampling frequency is twice as large than our bandwidth, means I'll draw that on the top. So that's the omega. This is when time equal to 0. This is our original signal bandwidth. So that's our omega b, negative omega b. If we do the sampling, what will happen is all the signal here, frequency, every when we increase this n from 0 to 1, 2, 3, so every one of these n will put a omega s on top of original omega, which means you have another one over here. This is our omega s. Then you have another one over here. This is 2 omega s. So if our omega s here is twice larger than omega b, means this width is omega b, omega b. If it's twice as larger than omega b, means this part, this signal, this part will be separate from this part. If our omega s is smaller than the twice of omega b, then it will be like this case. So these two actually overlap to each other. Okay? Because sampling will create kind of a train of the frequency from the basic frequency. It's always have mapping every multiple of the sampling frequency. You add on to that to the base frequency. So that's why our sampling frequency must be large enough. So when we convert this signal back to time domain, or if you want to compare this signal to some other signal, we are able to only take this part, and this can be recovered as our original signal. If this happens, if in the bottom this case happens, this little area, because the next sequence actually overlapped over here, then you go back to time domain, this will cause alias, and this part will cause in trouble. You can't get to the original signal anymore. So to summarize, after the sampling, our new frequency becomes our existing frequency within our bandwidth plus minus n times of the sampling frequency. So n can be go from 0, positive, negative 1, positive, negative 2 until positive, negative infinity. So we have a train of the frequency rather than the existing frequency omega. Okay? That's why we have to make sure this omega s is larger than the twice of the largest omega in the system. Okay? Otherwise, we'll have alias. So here is some summary for the alias. Refer to two continuous signal, or we call it sinusoid. So it's a kind of sine wave or cosine wave. Have different frequency. However, after the sampling, they shows up the same. Means your signal is aliased. Okay, and means we can't distinguish what our original signal is. This is an example of two sinusoid having alias here. So you get two signal, one with 1/8 Hertz, the other one with 7/8 Hertz. And if they are both sampled at 1 Hertz, so one is 1/8 Hertz, this blue one, the blue one is 1/8 Hertz. The red one is 7/8 Hertz. And the sampling rate is very slow, use 1 Hertz. And we know that to sample all those two, if the we need to set the bandwidth as the highest frequency. So we have to be like at least twice of this as our sampling frequency. But here, this 1 Hertz is only a little bit larger than the bandwidth. So we're expecting some alias. If you look at the signal here, you can see on these sample points, you cannot really tell is our original signal 1/8 Hertz or our original signal is 7/8 Hertz, because both of them were shown. This is another example, very typical. If we have a sine wave, if we look at the frequency domain of that signal, so you got, if we look at the frequency bandwidth, now we have to find a way to solve the problem, because our signal is always going to have high frequency noise, and most of the time we don't know the noise, like how high this noise is. So the simple solution here is put a filter before we do the sampling. Okay, we call this anti-alias filter. It can be very simple as first order low pass filter, just a first order low pass filter. Very simple, just to get rid of all the high frequencies. And the bandwidth of the filter, the bandwidth of this filter will be half of your sampling frequency. So make sure, if we do the sampling, this is our omega s, negative omega s, make sure there's no signal within or outside, no signal outside. So you got something curve within, the next curve is within, so it don't get alias back to the original signal. So that's the minimum we choose for the anti-alias filter. Okay. Physically, the location of the filter is right before the sampling. So these two actually go together. And this way, then we can make sure any signal go to this sampler is within certain range that limited by the filter. So there's no high frequency signal can get here. This is the previous example. 1 Hertz signal with 60 Hertz noise over here. As we said, we need to have an anti-alias filter in front of the sampler, and used to be 28 Hertz. So if say we pick 3 Hertz, this is already quite high compared to the useful signal we're having. So 3 times the useful signal we're having. So after the filtering, the signal become very clean, like this. And we do the sampling, or the samples looks like a sine wave as well. So in this way, the 60 Hertz signal, over here is already get rid of. So that doesn't exist. And so if the high frequency doesn't exist, with 28 Hertz, this is almost 9 times faster. So we won't have any aliens in the signal. So this actually looks like a sine wave, very much like a sine wave. We address the aliens problem through introduce a low pass filter. However, this low pass filter will introduce time delay to the system, and normally time delay will cause system to be less stable. So we'll get system less stable. So when we design the system, we have to design with a little bit more stability in our mind. Normally we have to give the system a little bit more phase margin in our mind. And then because of this filter, we'll reduce that margin later on, then we can get what we want. So another part, so this is just for the sampling. Another part, of course, delay is zero odd hold. And this also causes certain delays. In this one, the blue one is the continuous time signal, and zero odd hold is this green one. Okay, so actually we don't have the continuous signal. All right, this doesn't exist. We have this digital signal instance, which we hopefully wanted to get this blue one. However, using this zero odd hold, what we got in average is this red one. Okay, so you can see every instant the difference from what we expect to have, the blue one and the red one here, the difference is half of the sampling time. So the zero odd hold will create a delay of half of the sampling time. If we put that into phase margin, or in the radians, it is about omega t over 2. So it just multiply with omega. Okay. It's a delay, so it's a negative. So reduce the phase. It's a lag. You can see it's a lag. So to summarize, we have to consider the effect of sampling and also the effect of zero order hold. So sampling creates a first order filter causing some delay, and zero order hold cause a delay of half of the sampling time. So how do we select the sampling rate, sampling frequency? So this is not a scientific kind of must do equation. It's a kind of recommendation. Normally we want to say higher sampling rate. The higher the sampling rate, to a certain extent, we don't even need to consider it's a digital system. We can just use it as continuous time system, because when the sampling rate is extremely high, the delay caused by those filters and zero order hold all become very, very minimal. You can ignore those digital effects. However, that will introduce a lot of cost for the computational time. You have to have a very computational powerful computer to handle that, because every single instant during the sampling period, so every single sampling period, say if you have 1000 hertz, means sampling time, the sampling period is only 0.001 second, so 1 millisecond. If that's the case, you have to do all your calculation, all your mathematical control theory calculation within that 1 millisecond, and the system needs to kind of run with that kind of frequency. It is very, very demanding, and in many cases it's impossible. So you have to get a compromise. Like we don't want to go to extremely high sampling rate. We get a sampling rate that's high enough to give us a good enough result. So that's always a trade-off, a compromise, we'll see in this sampling rate selection. Okay. So based on previous rules, we know the sampling rate must be at least twice as the bandwidth, and the actual sampling rate we use normally is much higher than this. So a rule of thumb is we select our sampling frequency about 20 times to 40 times of our bandwidth. Okay, so in this case, we got quite comfortable. That's very far away from the alias situation, and it's not super high to like milliseconds, so we can't really do the calculation. So that's what we're going to do. So there's nothing kind of hard limit. You must choose certain frequency for your sampling, but there's a range, and that's just a normal rules. In some extreme situation, you might even go out of this range, but generally that's what we do.